Hello, welcome to this video series where we will take a journey through the solar system. We will explore the space we live in, focusing mainly on the latest advances currently being made in research in cutting-edge astrophysics. And we are living in an incredible era where great discoveries are being made with many space missions and other investigations in recent years that are also opening many new questions. And that is one of the objectives we set for ourselves in this series. We specifically want to talk about everything that is still unknown, about those mysteries. We are just beginning to glimpse those pieces of knowledge that we still have only as loose pieces of a much larger puzzle that we are still trying to fit together. Along the way, we will talk about ancient rivers and oceans that evaporated millions of years ago, solar storms that ravaged planets, and cryovolcanoes on icy worlds. But above all, we will talk about the origin of life, the big questions about how it all started and why we are here. In this series, we will have a guiding thread related to astrobiology. Astrobiology is the science that studies the problem of life in the universe, and well, today it is a discipline that surely has many more questions than answers. But many of those questions begin here, in our own solar system, at what would be the shore of the cosmic ocean, as Carl Sagan would say. In this first video of the series, we are going to start with the Sun, which, well, we all know is the king star, the one that dominates everything in the solar system. To give an idea, more than 99% of the mass of the entire solar system is in the Sun, but it's not just a matter of mass, it's also the main source of energy, providing light and heat, and it also causes the solar wind, magnetic activity, and many other phenomena that we are still beginning to understand. The Sun was born along with the rest of the solar system about 4.5 billion years ago. It formed in a molecular cloud, one of many in the galaxy, and began to collapse under its own gravity, possibly also disturbed, surely by some external factor. First it forms a rotating disk. That disk flattens, rotates faster and faster, and in the center it compresses due to gravity, accumulating the material from the cloud there. We do not know where that cloud is today, if it still exists, or in what part of the galaxy the happy birth occurred. Surely other parts of the cloud gave rise to other stars, which are known as the Sun's sisters and are still being searched for. There is even a candidate proposed out there, a star that is thought to possibly be one of these lost sisters of the Sun, but it is very difficult to know for sure. In fact, we may never know if these other sisters exist or where they might be found. But what we do know is that in that disk, the Sun formed in the center and the planets around it. The Sun began to shine with its thermonuclear fusion reactions, which, mind you, is not the same type as the nuclear reactions we can do on Earth. We do fission while the Sun does fusion. Yes, they seem very similar. Someone must have found it funny that there is only one letter of difference, but they are two completely different things. They have nothing to do with each other. In the coming decades, maybe in 30 or 40 years, depending on the investment we dedicate to it, we will surely have been able to master fusion energy. And then we will have a clean, safe, and very abundant energy source, practically inexhaustible. And that will be the moment, I believe, that will mark a before and after in human civilization. We can even hope, we can think that our grandchildren will be the first generation to live in that era of energy opulence. The miseries will end, and we can imagine what they will do with that power. They will be able to clean the planet, recover everything that previous generations have polluted. They will be able to travel through space. Who knows what possibilities will open up from that moment. And that knowledge, the mastery of fusion, which is something so important for the future of humanity, is something that is very closely linked to the story of the Sun. And we will return to that topic later. But as I was saying, I would like to pick up the thread where I was saying that besides the Sun, the planets were also formed. That happened in the disk. That's why all the planets move in the same plane, and we call that plane the ecliptic. And beyond the disk where the planets are, there is a whole series of small objects, an infinite number of them, which we call the trans-Neptunians. And they are in regions that we call the Kuiper belt. It is the first region we have beyond the orbit of Neptune. We also have the scatter disk, and then beyond that, the Oort cloud, which surrounds the entire solar system. We will talk about all those objects in other videos of this series. But first, let's return to the Sun, which is the energy source that shines and feeds the solar system. The Sun is basically made up of the same chemical composition as that primordial cloud from which it formed. 90% of the atoms are hydrogen, which is the lightest atom, the lightest element in nature. It is just one proton in the center and one electron around it. And as I say, it constitutes 90% of the entire composition, both of the cloud, well, practically of the whole universe. And also in the case of the Sun, then practically 10%, about 9-point-something%, are helium atoms, which have 2 protons and 2 neutrons in the center, and then less than 1% of everything else, starting with oxygen, and then carbon, nitrogen, and, well, all the other elements that make up everything we have around us in very small amounts. Of course, when I say small quantities, I mean it's a small percentage, but the Sun is so enormously gigantic that in the end, even if the percentage is small, the number of atoms is huge. And how big? Well, to give us an idea, the Sun is about 1,000,000 times larger than the Earth. It is very large and very hot. The surface is at about 6,000 degrees, which is not much because inside where the reactions occur, nuclear reactions, those fusion reactions, it is over 15 million degrees. It turns out that this enormous ball of fire up there is not a fixed and immutable thing, but rather it evolves, it undergoes changes on many different scales, right? If we look at its surface, it turns out that things are happening there. Arcs form there, spots form, what we call sunspots, and sometimes there also occurs something like large explosions, gigantic eruptions that release enormous amounts of energy, and this is what we call activity, which can sometimes be violent and, as I said, eruptive and very explosive. I suppose you have heard of the famous solar storms, which is a topic that, especially in recent years, has been quite current. Really more than storms, they are like eruptions, they are large explosions that take place on the surface of the Sun and are bigger than a planet. And this also happens in a cycle. The Sun goes through a maximum and a minimum of activity every 11 years. And also, as far as we know, this cycle has probably existed throughout history, although sometimes it has been weaker and sometimes it has been stronger. Why? No idea. That is one of the mysteries we have about the Sun and its activity cycle. But, well, we know some things. Let's start there and then we'll look at the unknowns that still remain. To begin with, why is there activity on the Sun? Why does solar activity exist? Well, mainly because it is a magnetic system. It has very powerful magnetism with very vigorous magnetic fields that are generated inside the Sun and manifest on the surface. Essentially, a star is a plasma gas. Plasma is a state of matter that occurs when the temperature is very high and atoms break apart. The temperature is so high that electrons are stripped away, and we are left with protons on one side, because remember that 90% is hydrogen. We have protons on one side and electrons on the other side, some charged positively and others negatively. In reality, the situation is more complicated because on the surface the temperature is not high enough for all the elements to be fully ionized. But, well, for now let's imagine it like this as a first approximation. Let's imagine that it is made of basically a gas of protons and free electrons. And then, in addition, it turns out that this plasma, which has an electric charge, is subjected to tremendous brutal movements. For example, there is differential rotation. The core of the Sun rotates faster than the surface, 3 times faster. The equator rotates faster than the poles, and then in addition, there are also global currents, like the meridional circulation, which goes on the surface from the equator to the poles. And then we also have convection, which is a bubbling movement that causes hot material coming from below to rise, reach the surface, cool down there, and fall back. And this convection occurs in something like the outermost layer, about 25% of the outermost part of the sun's radius. Well, I mean, after all these movements, electric charges, which are also movements of kilometers per second and tens of kilometers per second, even in some cases reaching hundreds of kilometers per second, well, that generates magnetic fields. Whenever we have moving electric charges, we have magnetic fields. So the sun is a dynamo of unimaginable size. It's hard to grasp the scales of the phenomena we're talking about because consider that a sunspot, which we see as so tiny on the sun, is larger than the Earth. That a magnetic arc we see rising over the solar limb can be dozens of times larger than the entire Earth. So we are talking about phenomena on a planetary scale, even larger in terms of the size of those electromagnetic structures. And here we encounter something totally incredible, which is what we call, well, it's called magnetohydrodynamics, forgive me for the word, which is usually abbreviated as MHD, let's say MHD for short, because the word itself is really cool. I love it. And it turns out that when these magnetic fields start interacting with the plasma, which we remember is made of electric charges, well, physics works wonders. To give you an idea, these are the basic equations of MHD. To begin with, there is a situation we call a frozen field. And this frozen in field means that the plasma and the magnetic field lines couple, can come together, so that the matter is forced to move only along the magnetic field. It is forbidden for the matter to move perpendicularly to the magnetic field. But of course, no, let's remember that the plasma is subjected to movements, to brutal movements as well. Do you remember what we said about convection, differential rotation, and this, right? So that plasma is moving, but at the same time it is coupled with the magnetic field. Then two things can happen. Either the plasma dominates or the magnetic field dominates. Well, or there is a third possibility, which is that neither dominates, and then we are in an intermediate situation that is very complicated, and it's better to leave it aside for now. But if we consider the two situations where one of the two dominates, then what happens is that if the magnetic field dominates, the magnetic field lines configure themselves as they please, which usually tends to be forming arcs. And in those arcs, which have two poles, a north pole and a south pole, like any magnet, well, there the matter is forced to move as if it were threaded along those magnetic field lines. It can only move along the arc, and this happens in the higher layers above the surface, and that's why the solar corona has an arc shape. By the way, something similar occurs in the Van Allen belts of the Earth. Van Allen belts, not Van Halen. What happens there is the charged particles are trapped in the Earth's magnetic field and forced to move only along the Earth's magnetic field. Well, there can also be another situation on the sun where the plasma dominates and then the plasma moves as it pleases with these convection movements and so on. And as it moves, it drags the magnetic field lines and tangles them. It's really impressive. Well, in addition to this frozen in field effect that we have been observing, there is another effect that occurs in magnetohydrodynamics, and it's important to understand in order to interpret what we see on the sun. And it turns out that the magnetic field lines behave as if this is not true, but as if they were elastic. This means that they present resistance to being bent. This obviously isn't really the case. We are making an analogy because magnetic field lines are not a real object. They are a mathematical construct to understand electromagnetic forces. But in magnetohydrodynamics, the field behaves analogously, as if those magnetic field lines were a real object and as if they were elastic. Let's do a small experiment to understand it. Here we have a small spring that I don't know if it will be very useful for what I want to illustrate, bought at the dollar store. Well, we say spring, but in other places they call it a coil, as you can see. I'm also good with languages. I handle 6 million forms of communication. Well, we can imagine that this spring or coil represents the lines of field in a solar prominence. Let's suppose that I have them anchored on the surface, that the North Pole and the South Pole are anchored on the surface. And these lines form an arch-shaped structure, and the material is forced to move here.
Let's see if I can
grab them with one hand. And the material would be forced to move along these lines, which would be the magnetic field, okay? Now let's give this analogy another twist, literally. Why? Because at the base, at the feet of this spring, we have, as I mentioned before, movement. In the upper layers, the magnetic field dominates, and the spring tells the matter where it has to move. But in the other upper layers, as on the surface, como se get Jan Puente, where it is in contact with the solar surface, the material is moving as if there were no magnetic field, and it is moving it and dragging it, so it is twisting it. Therefore, this is spring is twisting at the base, and that generates a tension that propagates to the higher layers. And as I keep twisting this material below, not much will come out, but you can imagine that tension accumulates in the higher layers until it reaches a point where it breaks. And all the accumulated energy is violently released, and all the plasma inside is violently expelled into space. This is somewhat the analogy we make when we say that there is an elastic behavior of the magnetic field lines. And this analogy, moreover, can be quite extrapolated because the way we study it and study the potential energy of the magnetic field is very similar to the potential energy of a spring, which accumulates energy as we twist it. Energy accumulates, which in the case of the spring is elastic potential energy, but in the magnetic case, it is magnetic potential energy. Well, as I say, there comes a moment when we accumulate that energy until the spring breaks and all that potential energy is released instantly. The analogous process in magnetohydrodynamics to the spring breaking is what we call magnetic reconnection. It is a very interesting phenomenon that is still not well understood, but somehow it occurs when the magnetic field is under a lot of tension and is able to find another configuration that is very similar but with much less energy. So, as I say, in ways that are still not well understood, it is capable of instantly reconfiguring to that lower energy form. This is prohibited in ideal MHD, and to understand it, more complex theories than the ideal are needed, and that's why it's still well understood somewhat poorly. But what we do know is that it happens. We observe that from time to time, these springs on the sun, these magnetic arcs break, and that causes a violent reconfiguration of the magnetic field. And it releases a terrible amount of energy, like the equivalent of millions of atomic bombs detonated simultaneously in less than a second. And these eruptions, as I said, can project a large amount of solar material into space. They are true plasma projectiles known as coronal mass ejections. Nowadays, we think that the way the impact planets can play an important role in the evolution of planetary atmospheres and even in habitability. And a paradigmatic case is Mars. 4 billion years ago, Mars was a habitable world. It was covered by oceans of liquid water. Possibly, at that time, the conditions on Mars were better than on Earth for life to emerge. However, Mars quickly lost those conditions and ceased to be habitable. But we will talk more about that topic in another video of this course. I just wanted to mention that it happened due to solar activity. The solar activity stripped Mars of its atmosphere and abruptly ended its potential habitability. Many of the exoplanets we know that we have discovered orbit around red dwarfs. And this is because these planets are easier to detect, and also because red dwarfs are by far the most abundant stars in the galaxy. And today there is an important debate in the scientific community about whether those stars are suitable for life, because it is thought that they have very violent activity, much more violent than the sun. And the resolution of this debate will largely depend on the possibility of finding extraterrestrial life, I believe, because if what happened on Mars is representative of the geological history of planets, then the chances of life emerging on a planet would be quite a bit lower. On Earth, solar eruptions can have effects on our technological society. In 1859, what is called the Carrington event occurred. Of course, at that time, there was hardly any technology that could be affected, but for example, the telegraph network collapsed in the United States. Auroras were seen at latitudes as low as the Caribbean, or here where I live, in the Canary Islands. It is said that in England, one could read at night by the light of the auroras. We do not know what would happen today if something like that occurred, but the few stories that exist suggest it would have catastrophic consequences, with widespread blackouts, collapse of computer systems, electronic systems, and, in general, economic damage worth trillions of euros. Billions with a B. I will talk more about this in another video. The point is that the current frontier in the study of solar activity and MHD and these eruptions is mainly at a small scale. Understanding what happens at the smallest scales, these mass ejections we have mentioned and these flares that occur could also be happening on a small scale in a widespread manner, especially across the solar disk, in explosion too small to be seen individually. The idea is that they will be occurring over the entire surface and could partly be responsible for the complex behavior of the solar wind. Right now, we are living in a truly fascinating time for the study of solar activity. In this decade, 4 major projects of space probes and ground-based telescopes will coincide. In space, we have NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter. And here on Earth, the new KIST Solar Telescope in Hawaii has just seen its first light, and we expect that in the coming years, the European Solar Telescope will be built here in the Canary Islands. And speaking about space missions, there is a curious detail that might sound a bit counterintuitive, but I find it interesting to mention, and that is that it is very difficult to send a probe towards the Sun into the inner solar system. Going to the Sun is very difficult. It is much more difficult than going outward towards the outer solar system. And the reason is that when we launch a rocket, anything that leaves Earth inherits the same speed that our planet has around the Sun, and the Earth moves at 30 kilometers per second in a direction perpendicular to the Sun. That is something like 100,000 kilometers per hour. So even if you aim your rocket directly at the Sun, it will end up moving sideways at 100,000 kilometers per hour. So we cannot send a rocket to the Sun even if we want to, because it will veer off to the side, and what will happen is that it will end up in orbit around the Sun. The only way we can get something we send to end up falling towards the Sun and approaching it is to remove that speed. That is, if the Earth moves at those 100,000 kilometers per hour, we will have to launch our rocket backwards in the Earth movement against the Earth movement at those 100,000 kilometers per hour, 30 kilometers per second. It turns out that as of today, we do not have rockets powerful enough to do that, so we do not have rockets powerful enough to go to the Sun from Earth. The only way it can be done, and what these space missions I mentioned take advantage of, is by using what are called gravity assist maneuvers. And what it's about is going to another planet, passing close to another planet, and using its gravity so that the gravity of that planet slows down our probe, takes away that speed, and in that way it can fall towards the Sun. These maneuvers have been used before to accelerate our spacecraft outward, but also, as I said, they can be used to slow them down and make them fall inward. About this, I can tell you the anecdote that the Parker Solar Probe, which is the probe that has come closest to the Sun and will continue to get closer in the coming years, the original plan of the mission was to first go outward, go to Jupiter, to make a gravitational encounter with the giant planet, with Jupiter, and use Jupiter's gravity to slow down the probe so it could quickly fall towards the vicinity of the Sun. It seems paradoxical, but the fastest way to go to the Sun is to first go to Jupiter, let it slow us down, and then the probe can fall directly towards the Sun. Unfortunately, it could not be done because a series of changes occurred in the mission, and in 2003 specifically, there was a series of, a budget cut that forced the entire mission to be redesigned to reduce costs. And in that new version, in that new revised mission, well, the trajectory had to be redone, and the encounter with Jupiter was changed. It was too expensive to make a spacecraft go to Jupiter and then fall into the sun, so that was replaced by making encounters with Venus. And what it did was pass by Venus several times, so that each time it shortened its orbit more and more, and the successive passes around the sun became increasingly closer. In this way, well, the mission changed quite a bit, and it couldn't get as close to the sun as originally planned. And there were also cuts to the thermal shield and other various aspects of the mission. But well, the important thing is that in the end, the mission has moved forward and is there, and is already producing results. In fact, a similar situation has also happened with the solar orbiter of the European Space Agency, which will also make flybys of Venus to perform these gravity assist maneuvers, slowing down its path and thus being able to approach the sun. Surely in the coming years we will learn a lot from both these probes and the large super telescopes being built on Earth. Surely we will be able to better understand magnetic reconnection, the solar wind, and the activity not only of the sun, but also of other stars in general. We will continue talking about the sun and the solar system in the upcoming videos. In fact, in the next video, I look forward to talking about Mercury, the messenger of the gods. See you, don't let me down.